In my first video about basic electricity, you learned that current is basically the flow of electrons in a wire, and the term amps or amperes refers to how many electrons are flowing past a certain point per second. In this video, I'm going to first tell you what voltage does, then I'm going to explain what voltage is. There's an important difference. Okay, the super simplified explanation of voltage is that volts push current around an electric circuit. Voltage behaves like a pushing force, forcing electrons to start moving around, which creates an electric current. Okay, I want to show you an example. Over here I have an electric motor with some wires connected to it. This fancy thing is an adjustable power supply. It allows me to create nearly any voltage I want, which is useful for designing circuits, but you don't need one of these to start learning about electricity. You can just use batteries. The voltage I'm generating will be shown here, and the fun thing about this power supply is it can automatically measure how much current is flowing, and that's going to be shown here. I want you to see how when you increase the voltage going to the motor, more current flows. If we start out with the power supply set to 0 volts, the motor doesn't do anything. Now let's set the power supply to produce 1 volt. Immediately you can see that there's current flowing, roughly 1.8 amps. And when there's current flowing, energy can flow from the power supply to the motor. Now let's increase the voltage to 2 volts. Now that we have a bigger pushing force, more current is flowing, 2 amps. So more energy is flowing through the motor, so obviously it's going to turn faster. And the more I crank up the voltage, we get even more current and the motor speeds up. Okay, that's just one example of what voltage does. You can use a voltage source to power motors, light bulbs, electronics, and other things. Another important example of what voltage can do is carry useful information. You can use different voltages as electrical signals that represent data. In this example, 0 volts or 5 volts represents binary zeros and ones in a communication system. Now, this is way more advanced than what I want to talk about in this video. I just want you to understand that sometimes voltage is used to power things that draw high amounts of current, but you can also use voltage as a signal, and almost no current flows at all. You just create the changing voltages with a transmitter and detect the changing voltages with a suitable receiver. Now remember, the whole volts push amps thing is just a helpful simplification. What's really going on here is that there's a chemical reaction inside this battery that's creating a voltage. This side of the battery is more negatively charged than the top of the battery. Negative charges repel negative charges, so this side of the battery will push electrons away from it. Electrons push other electrons, current flows, and the electrons on the top side get attracted to the positive side of the battery, and everything flows in a complete circuit. Okay, I've been talking about what voltage does and how you can use it. Now let's talk about what voltage actually is. Voltage is a difference in electrical potential energy per unit of charge between 2 points.
What?
Okay, there's a lot to cover here, so let's break all these words down into their basic definitions. Let's start out with the words potential energy. Forget about hippies and feelings for a second. The actual scientific definition of energy is the ability to do work. The work could be moving something, heating something, things like that. We say something has potential energy if it has the potential to do work. For example, this stretched elastic band has elastic potential energy. It's not doing anything right now, but it has the potential to do work. If I released it, the elastic potential energy would be converted into movement, which will propel the piece of paper into my target. This battery has electrical potential energy. It's not doing anything right now, but it does have the potential to do work. There's a chemical reaction inside it that creates electrical potential energy, and if I connect this light to this battery, we form a complete electrical circuit. Current will flow, and a little too much current flowed. I guess we need to learn a little more about electricity before we try that again. Anyway, those are some examples of potential energy, and it's important to know that we measure energy with units called joules. Joules can be used to describe the amount of energy it takes to do a lot of different things. 1 joule is enough energy to power this flashlight for 1 second. 3 joules is enough energy to power this flashlight for 3 seconds. And 90,000 joules is the energy required to power this microwave for 1 minute to make a cup of tea. We'll talk more about energy in joules later in the video. Okay, so now you have an idea of what electrical potential energy means. What does this unit of charge mean? Well, do you remember how I was saying that electrons are negatively charged particles, and 1 amp is 6.24 times 10 to the power of 18 electrons flowing per second? That's a really awkward number, and engineers hate using it. Instead, we use a standard unit of charge called the coulomb. The total charge on 6.24 times 10 to the power of 18 electrons is equal to 1 coulomb of charge. And since electrons have a negative charge, this charge would be negative. You can see now that it's much easier to just say 1 ampere is equal to 1 coulomb of charge flowing per second, and 2 amps is 2 coulombs flowing per second. Now let's tie these two concepts together. When we talk about electrical potential energy per unit of charge, we mean that a certain number of joules of energy are being transferred for every unit of charge that flows. For example, let's say this is a 1.5 volt battery. That means that for every coulomb of charge that flows from the battery, 1.5 joules of energy are being transferred. 1.5 joules of chemical energy are being converted into electrical potential energy. Then, this electrical potential energy, or voltage, pushes electrons around the circuit, and for every coulomb's worth of electrons that flow, 1.5 joules of energy are getting delivered to the light bulb and converted into light and heat. Now let's go back to my example with the motor. With the power supply set to 0 volts, no current can flow. But with the flick of a switch, now the power supply delivers 1 volt, or 1 joule per coulomb. And over here, the power supply is measuring the amount of current flowing through the motor. It's roughly 1.8 amps. 1.8 amps means that 1.8 coulombs are flowing from the power supply every second, and for every coulomb, 1 joule of energy gets transferred. So 1 volt times 1.8 amps means that 1.8 joules of energy are flowing through this motor every second. If we increase the power supply's voltage to 2 volts, the higher voltage pushes more current, and now we have 2 coulombs per second flowing. 2 volts multiplied by 2 amps means that 4 joules of energy are flowing through this motor every second. And of course, with more energy flowing through the motor every second, obviously the motor is going to do more work and spin faster. Okay, now that you understand energy per coulomb, let's go back to our definition of voltage and talk about this part. Voltage is the difference in electrical potential energy between 2 points. In other words, voltage is always relative. We all say this is a 9-volt battery, but that's not 100% correct. What we're supposed to say is that there's an electrical potential difference of 9 volts between this negative terminal and this positive terminal. There's a difference of 9 joules for every coulomb that flows out of the battery, and that's what makes this a 9-volt battery. Over here, in casual conversation, we might say that this is a 5-volt USB port. But what we really mean to say is that there's 5 volts between this positive power pin and this negative power pin. These two pins are used for sending digital messages, and there's a rapidly changing 3.3 volts between them, which carries the information. So voltage is always measured between 2 points, and this is why voltage is also sometimes called potential difference. That's right, voltage can sometimes be called potential difference, tension, and a lot of other names. No wonder people get confused. Okay, that was voltage. My next video will be linked over here. In the meantime, subscribe, thumbs up, Twitter, Facebook, website, yada yada yada, you know what to do.
One of the most useful ways to analyze a circuit is to look at the relationship between voltage and current. And there is one component that makes that analysis very simple. This is the resistor. Its function is very simple. It restricts the flow of electrons. Now, impeding current may seem a little silly, but there are times you may want to reduce the current flowing to a component or lower the voltage going to some sensitive electronics. In an ideal world, the resistor creates a linear relationship between current and voltage. And if you know 2 of those 3 things, voltage, current, and resistance, you can easily calculate the third. We'll see how to do that later, but for now, let's see how a resistor works in a circuit. In the previous episode, I showed how moving current can be represented by steel balls in a tube. If one steel ball represented 1 electron, then it would take around 6.25 times 10 to the 18th steel balls to move past a point per second to make 1 amp. Since I don't have billions of steel balls in a massive plastic tube, we need some other way to show electric current. As it turns out, fluids like air and water actually make a pretty good representation for electric current. What I've got here is a circuit, not of electricity, but of water. I've added some mica powder and blue food coloring to it so you can see the water flowing more easily. In our little demo, the pump represents a power supply like a battery or a wall adapter that pulls water up from a well and gives it the push needed to move around the circuit. The tubes are like wires. They provide a path for the current. The water pressure in the tubes corresponds to voltage, and the amount of water moving through a tube corresponds to electrical current. Note that we're using conventional current, so the water is flowing from high pressure to low pressure. Amperes is coulombs per second, so in terms of water, that would be volumetric flow rate, something like cubic centimeters per second. What we've got here is the water analogy of a resistor. This is some steel wool shoved into a tube. You can see how all that material resists the flow of water, and there is higher pressure on the side the water is entering the resistor. The same holds true in electronics. There is a voltage difference between the ends of the resistor when current is flowing through it, and this is known as a voltage drop. Let's go back to the actual resistor component. If you were to slice one open, you would find coils or film of tiny wire or a solid core made of a carbon mixture. However it's made, the resistor acts to impede current. In 1825, the German physicist and mathematician Georg Ohm began experimenting with early chemical batteries and thermocouples to produce voltages. By varying the size of wires used to complete the circuit, he determined that voltage and current were proportional. In math terms, that means the voltage between 2 points is equal to the current flowing between those points times some number, and that number is known as the resistance between those points. Ohm's law is often written as V equals IR, or voltage is equal to current times resistance. Lucky for Mr. Ohm, the unit for resistance was named after him. The ohm is abbreviated with the Greek letter omega. With this information, we can begin to analyze circuits. As an example, we'll connect a resistor to a power supply that provides 3 volts. The electronic symbol for a resistor is a zigzag with 2 terminals. It represents a more complicated path and therefore reduced current flow. Note that it doesn't matter which way we connect the resistor, it will do its thing regardless of orientation. We will connect the terminals of the resistor to the positive and negative terminals of a power supply that's been set to act as a voltage source. A voltage source, similar to a battery, will supply as much current as needed to maintain a particular voltage between the terminals. Now that we have a circuit, current will flow from the positive terminal of the voltage source through the resistor and back to the negative terminal. The power supply will be set to 3 volts, and it will also tell us how much current it is supplying. With that information, we can determine the resistance of the resistor. Let's try it. Alright, I've connected the resistor to this power supply using some alligator clip leads. You'll notice I used red for positive and black for negative terminals connected to the power supply. When I turn it on, it reads about 3.03 volts. And it also tells me that about 0.03 amps are flowing from the positive terminal through the resistor and back to the negative terminal. Let's see if we can use this to calculate the resistance of this component. Using Ohm's law, V equals I times R, we can plug in the values from our readings. So 3 volts equals 0.03 amps times R. Using a little bit of algebra, we can calculate R. And we get R equals 101 ohms. Now that we've mathematically determined that we have a 101 ohm resistor, let's check our work. This is a digital multimeter, and it's one of your best friends when analyzing a circuit. Most basic models can do things like measure voltage, current, and resistance. We'll set this one to measure resistance and touch the leads to the ends of the resistor. As you can see, it's reading about 100.2 ohms, which is pretty close to our math results. Since this is labeled as a 100 ohm resistor, we'll call it good enough. If you're wondering why the measurements and calculations didn't come out to be exactly 100 ohms, that's because there are inconsistencies in the manufacturing of resistors, which of course means that the resistance can be a little bit off from the listed value. Additionally, there's resistance in the wires and potentially the power supply itself, so measuring the voltage between the terminals of the power supply could be a little bit different than measuring the voltage between the terminals of the resistor. Back to our water demo, we see that the steel wool, much like the resistor, restricts flow. If we were to add an even denser material like a sponge, the water flow would decrease even further. The same holds true in electronics. For a given voltage, as resistance increases, current decreases. Knowing Ohm's law by heart, V equals IR, will get you through many troubles in the electrical world, so it's one of the few equations I recommend committing to memory. Besides, it's only 3 letters. As it turns out, by resisting current, electrical energy gets converted to heat. In the next episode, we'll learn how to calculate electrical power and figure out how to do something useful with all of that heat from resistors.
Aha!